Hello students, welcome to Saras's classes. In this video, I will be solving the following question from ISS 2017 paper 3. Now here we have to discuss the following allocations of sample size in stratified random sampling. Now let's start with the first one, that is proportional allocation. Now suppose we have a population of size say capital N, which is divided as the following stratas. Now the sample size or the number of units selected from each strata, it will depend upon the size of the strata, that is, suppose NH, capital NH. So suppose capital NH, it is the size of population size of hth strata, and suppose small nh, it is the sample or sample size, it is the sample size drawn from the hth strata. Then this nh, this is proportional to capital NH, that is the size of the sample, it is proportional to the size of the population of that strata, that is small nh, it is proportional to capital NH, or we can write small nh is equals to k into capital NH, where this k is a constant, or so it is a proportionality constant, So NH is equals to K into capital NH. Now if we take summation on both the sides, we would get summation H runs from 1 to L. So where L is the number of strata, this is equals to L. So summation H runs from 1 to capital L, small nh, this is equals to K into summation H runs from 1 to capital L, capital NH. So which would imply, now summation of small nh, it is nothing but the overall sample size, that is small n, is equals to K into the summation of capital NH, it is nothing but our overall population size. So it is small n is equals to K into capital N, or the K, this is equals to small n by capital N. So we would have our NH, this is equals to small n by capital N into capital NH. So this is the allocation rule, which is called proportional allocation. Proportional allocation rule. Now next is Neyman's allocation. Now in Neyman's allocation, along with the size of the stratum, population size of the stratum, we also take into consideration the stratum variability. So in proportional allocation, we only take into consideration the size of the population. Here we take into consideration the size of, or population size of stratum plus the stratum variability, which is denoted by sigma h square. So in Neyman's allocation, we take into consideration both population size of stratum and stratum variability, which is denoted by sigma h square. So here what we would have is that our small nh, that is the sample size drawn from HH strata, it is proportional to capital NH into sigma H, where this capital NH, it is the population size of HH strata, and sigma H square, it is the stratum variability. Stratum variability. Now, so this would imply that NH, this is equals to, so our NH, this is equals to K into capital NH into sigma H. Now if we take summation on both the sides, it would get summation H goes from 1 to capital L NH, this is equals to K into summation H goes from 1 to capital L NH into sigma H. Or we would have our K is equals to, or our K would be equals to small n, which is equals to summation H runs from 1 to L NH divided by summation H goes from 1 to capital L NH into sigma H. So this is our value of K, and hence our NH would be equals to n divided by summation H runs from 1 to capital L capital NH into sigma H, this into capital NH into sigma H. So this is our Neyman's allocation rule. So this is the Neyman's allocation rule. Now the third one is optimum allocation with linear cost function. So suppose we have a cost function C is equals to C naught plus summation H goes from 1 to capital L CH NH, where the C naught, it is the constant cost, that is the constant cost, and CH, it is the cost associated with the sampling of HH strata. So CH হচ্ছে cost associated with sampling from HH strata. So CH is the cost associated with sampling from HH strata, and C naught is like constant cost, which would be overall generated, and it does not depend upon which strata. Now, so we have this cost function, and we have to select NH. So we have to select NH such that variance of x bar st, so this variance is minimum. So the variance is minimum for the given total cost. So for the given cost function, we have to find the NH such that the variance x bar st, this is minimum. Now let us define a Lagrangian function f, which is equals to variance of x bar st plus lambda into C naught plus summation H goes from 1 to L CH NH minus C. So here this lambda, it is a Lagrangian multiplier. So it is a Lagrangian multiplier. So we get our Lagrange function. Lagrange function as f is equals to variance of x bar st plus lambda into c naught plus summation h goes from 1 to L chnh minus c. So this is our Lagrangian function. Now we are substituting the value of variance of x bar st, where variance of x bar st, this is equals to the variance of x bar st, variance of x bar st, this is equals to 1 by capital N square into summation h goes from 1 to L nh square into 1 minus small nh divided by capital NH into sigma h square divided by small nh. So variance of x bar st is equals to this. So we will have our f is equals to 1 by capital N square into summation h goes from 1 to capital L nh square into 1 minus small nh divided by capital NH into sigma h square divided by small nh. Now plus this part, which is lambda into c naught plus summation h goes from 1 to capital L ch into nh ch into small nh minus c. So we get this. Now we will differentiate it with respect to nh. So we will have df by dnh, which would be equals to, so this is equals to 1 by capital N square into, now here nh and nh would cancel out each other, so what would be left is capital NH square into sigma h square divided by nh square. Now since it is nh raised to a minus 1, so while differentiating it, minus 1 will come out. So minus 1 by capital N square into capital NH square into sigma h square divided by small nh square plus this term lambda into ch. Now when we equate it to 0, so when we equate this to 0, it would imply that nh, this would be equals to, so by equating this we will get nh is equals to 1 by root lambda into capital N into capital NH into sigma h divided by root over ch. So if we put this part, that is 1 by root over lambda into capital N as lambda dash, then we will have nh is equals to lambda dash into capital NH into sigma h divided by root over ch. So nh is equals to this. So here we can clearly see that our nh, this is proportional to capital NH sigma h divided by root over ch, as this lambda dash is a constant. So since it's a constant, therefore from this we can clearly say that nh is directly proportional to nh sigma h and inversely proportional to root over ch. Now what we will do is we will put this value in our cost function. So we will get c is equals to c naught plus lambda dash into summation h goes from 1 to L ch into nh sigma h divided by root over ch. Here what we are doing it, we are substituting the value of small nh with this. So let us consider it as delta. So we are substituting nh in our cost function using the equation delta. So then we would get C is equals to C naught plus lambda dash plus summation h would go from 1 to L ch into nh into sigma h divided by root ch. So C is equals to C naught plus summation h goes from 1 to L ch into nh. Here we are substituting this nh with equation number delta, so we will get this. Now from here we would get our lambda dash would be equals to C minus C naught divided by summation h goes from 1 to capital L nh sigma h into root over ch. So this is our lambda dash, therefore we would get our nh. So we would get our nh is equals to, from this equation delta, so from delta, that is substituting the value of delta dash here, lambda dash here, we would get our value of nh is equals to C minus C naught divided by summation h goes from 1 to capital L nh into sigma h into root over ch into nh sigma h divided by root over ch. So this is the value of nh, that is, this is the allocation rule known as optimum allocation rule. Optimum allocation rule.